Okay, so I'm Cristina Fernandes, and it's a pleasure to introduce Nicole Immorlica. Some of you might remember her appearance at a video from WIT, Women in Theory, where TCS ladies made a performance on an interesting version of I Will Survive. Nicole's research lies broadly within the field of algorithmic game theory. She is keen on using her scientific knowledge to better understand the human behavior. Her areas of specialty include social networks and mechanism design. Nicole received her PhD from MIT. She did 2 postdocs, one at Microsoft Research and another at CWI in Amsterdam. She was a professor at Northwestern University in Chicago. And since 2012, she works at the Microsoft Research New England lab. Nicole is part of the virtual chair team, so you can try to direct any suggestions on the system directly to her. She has collaborated with several researchers that we all know. Among other honors, Nicole was elected the 2019 chair of the ACM Special Interest Group on Economics and Computation. And today she's going to talk about incentivizing exploration with selective data disclosure. Welcome, Nicole.
Thanks for the introduction. As Cristina said, I'll be talking about incentivizing exploration with selective data disclosure. And this talk is based largely on joint work with Jiming Mao, who is now at Google Research, but at the time was an intern at Microsoft Research, Alex Lifkins, who's my colleague at Microsoft Research, and Stephen Wu, who is starting at CMU and was a postdoc at Microsoft Research when we did this work. So in the incentivized exploration problem, you guys are coming from the CS community, so you probably know very well the multi-arm bandit problem. The incentivized exploration problem is exactly that, but where which arms get pulled is chosen not by an algorithm, but by an individual, an agent. So we have a set of agents that are coming to the system one by one. They come just one time, they choose an action, and they receive a stochastic reward from an unknown distribution, just like in the multi-arm bandit problem. And then the agent wants to pick the action that's going to give them the highest expected reward. But there's a principal who's trying to coordinate the choices of the agents such that the agents in aggregate over the whole time horizon are receiving high rewards. And so applications of this might be buying products, for example. So you go shopping on Amazon and you want to buy a new gaming laptop maybe. And so this is a product you buy basically once every 5 years or something. So this is a short, like you're just trying to buy one product, and your payoff from the product that you select is going to be the quality of the choice. And you don't know whether the Dell laptop is better than the IBM Lenovo laptop, and so on. And so you're going to select a product, and you're going to buy that product, and you're going to get a payoff that's the quality of the choice. Another example might be choosing medical treatments. So maybe you have some sort of rare disease and you need to select what medical treatment you'll undergo, and the quality or the reward that you get from any medical treatment you choose are the health outcomes. And so what I'm trying to emphasize here in these two examples is that the value of a particular action to a particular agent is the same across agents. So there's a common value setting here. Everybody wants to get good health outcomes. Everybody wants to have high quality gaming laptops. And so in these kinds of settings, we often have a principal who's trying to coordinate the choices. Maybe if you're buying products, that's Amazon. If you're choosing medical treatments, that's your doctor and the health profession more generally. The kind of example you can use to have in mind throughout this talk that I'll use as motivation is recommendation websites like Yelp. So here I searched for pizza near where I live in Manhattan, and you can see Yelp came up with a bunch of options for me. There's Arturo's, it's a 4-star, 678 reviews and $2 signs restaurants. And the second choice in the list that Yelp presented was Prince Street Pizza, which has 3,463 reviews, 4.5 stars and $1 sign. And so, you know, Yelp here is the principal. Yelp is selecting which restaurants to recommend to me. And they're displaying them to me and trying to perhaps, you know, help me find a restaurant that is of high quality in order to make me happy with the Yelp service. And so in this setting, there's some trade-offs because Yelp, you know, wants to help me, but also wants to help all future tourists that are going to come and look for pizza in New York City, right? And so in order to maximize welfare across all of these users of Yelp, Yelp has to, you know, give each agent enough information to make the best choice for him or herself. So that would be like exploitation in the multi-armed bandit literature. But simultaneously, because Yelp doesn't know what the best pizza restaurant is, Yelp needs to provide incentives for agents to explore and take infrequently selected choices such that Yelp learns more about those restaurants. And so the difficulty here is that the benefits of this kind of exploration are only accrued by the future agents. Any individual agent would rather just take the best, the action with the best the best mean at the moment, right? So they want to take the best action given all available information that every agent only wants to exploit. But the principal would like some agents to explore, and in fact needs some agents to explore in order to give better recommendations to the future agents. And so there's a lot of prior work in this line of literature on incentivized exploration, and prior work is leveraging this information asymmetry or payments to induce an optimal amount of exploration. Instead, in our work, we're going to use what I call selective data disclosure. So the platform is going to choose which reviews to display to each individual user in order to try and influence their choice. But the platform is choosing which reviews to display based on when they were written, but not what they say. So in a sense, this reviews they present to me are unbiased. They're not trying to only show me good reviews of one restaurant and bad reviews of another. At the same time, the agents, I'm going to have a model of behavior, which I call frequentist. So these agents are going to select their actions based on the empirical mean and the number of data points. So they look at all the star ratings of all the restaurants and the number of reviews of each restaurant, and then they make some selection based on that information. And I'm going to require that their estimate of the quality of a restaurant gets asymptotically close to the empirical mean as the number of reviews grows. But within that confidence interval, they can make any assumption they want. And I'll get into the precise modeling of that later. So what we'll see is that there's a simple policy that's going to divide agents into focus groups and then collate their data to get low for all future agents to get low regret with respect to the optimal reward. And then we're going to also present an optimal policy that has some more complex interactions, which I'll hint at later on. But let me first start with a little bit of discussion of the background. And so in the multi-armed bandit literature, as you well know, it's exactly with the setup I've just described, but instead of having a sequence of agents that sequentially choose actions, there's a single centralized planner, and the planner is choosing the actions, and there's no incentive constraints because, you know, the planner wants to optimize the reward over the time horizon and not at any individual time step. And so there's many examples of where we study this in computer science that I'm sure you're familiar with, things like online ad placement, where you get a, the planner gets us a +1 if the ad was clicked. So they're trying to learn where is the best place to put an ad on a web page. Another example application would be algorithmic tuning. So I have many heuristics I could use for my problem, and every day I have to say schedule how I route my my UPS trucks, and so I choose different heuristics on different days and try to find the one that has the best value in the solution it presents. So these are the sort of historic applications of the multi-arm bandit, and if you aren't already familiar with this literature, I just wanted to take a moment to advertise my co-author's book, which I think is a very gentle and well thought out introduction to multi-arm bandits, published in the Foundations and Trends Journal in 2020. So the multi-arm bandit, this is a big literature. Let me be a bit more precise about the formulation that I'm going to build off of in the incentivized exploration setting. We have actions, or arms, as I will start calling them, a time horizon T. The planner chooses one arm in each time step, and the arm yields a reward from an unknown distribution. So there you could distinguish between Bayesian bandits, in which the planner knows has a prior over the distribution class for the arms, but I'm going to be working in the stochastic bandit setting, in which this distribution is unknown. We're going to assume bandit feedback, which means that only the reward of the chosen arm is observed. We don't get to observe the quality of a restaurant we didn't go to. And I'm going to assume IID rewards. So there's no contexts here. The rewards are drawn independently from a distribution that depends on the arm, but not on time and not on the agent that pulled the arm. The objective is going to be the standard regret objective. So we want to minimize regret, which is defined to be the optimal reward over the time horizon minus the reward that the algorithm receives over that same time horizon. And the sort of canonical theorem in this literature is that for stochastic bandits, the optimal regret is like root T, where T is the time horizon. I'm hiding here log factors, obviously. Notice that this means that the regret is sublinear in time, and therefore it approaches the reward of any Bayesian planner without using his or her prior. So this is a very strong benchmark. And the question is if we can get this kind of root T regret bound in the setting where we have these incentive constraints. So the classic literature says we can get root T regret if we have a centralized planner that's optimally trading off exploration and exploitation. But what if the planner can't dictate which arms get pulled, but can only make recommendations to agents that then make their own choices, like in the Yelp world? So that question is this line of literature that I think is really interesting called incentivized exploration. The question being, how can the principle induce exploration in these kinds of problem setups? And as I mentioned earlier, the idea in the literature, the predominant idea in the literature is that only the principle knows the rewards of the past arm pulls. So, it's not like when I go to Yelp, I have a microphone that I broadcast to all of New York City that I can say what my experience was. Instead, I write a review that is submitted to Yelp, and then Yelp does whatever it wants with that information, right? So this induces an information asymmetry because the principal, Yelp in that case, has information about the past arm pulls and their rewards, but this information is not passed on to other agents unless the principal chooses to do so. And so by leveraging this information asymmetry, the principal can induce an optimal amount of exploration by recommending exploration to each agent with some small probability and otherwise recommending exploitation. So in this policy, the principal will look at all of the information that has been collected so far, and with that now the principal knows they could say mimic the UCB algorithm by saying, okay, which arm would my algorithm want to pull if I were able to dictate which arm would be pulled. I'm going to recommend that you go to that restaurant with some small probability. And with the remaining large probability, I'm going to recommend you go to the restaurant that you would want to go to if you had access to all the information that I have access to. And the agent not being able to distinguish whether the recommendation was of the first type or the second type is therefore incentivized to follow it, because with high probability, it's a recommendation of what you would do anyway if you had access to all the information. And so in this way, the principal can get some amount of exploration from the population. The other sort of tactic that's been explored is to pay agents to do the exploration. So if I know how much value you expect to lose by doing this exploration, I can just pay you to do it, and you'll be incentivized to do it. So these are the main tacks that were studied in the past, and the way that they sort of state the problem and in the information with the first of these, where I'm trying to get agents to explore by using information asymmetry, what the principal does is they commit to a signaling scheme, which maps any history of rewards to a recommended arm. And then the agents sequentially choose the arms based on the prior in the signaling scheme. And as I discussed in the last slide, we can, without loss of generality, assume that this signaling scheme incentivizes agents to follow their recommendations. And then what the literature shows, and I think this is a really interesting result, is that you can still get this root T regret bound, even though there's these incentive constraints. So you can do as well as you could do with a centralized planner. Of course, the constants I'm hiding blow up exponentially in the number of arms, whereas they only blow up polynomially when you have a centralized planner. But the root T is the dependence on T is the same. And so that's kind of the main result in the prior literature, that we can get the same regret bounds up to big O with the incentive constraints of the agents. Now, what I thought about when I was following this literature is that the systems that these papers propose are not something I would ever actually recommend Yelp do, because they basically, what the systems propose is you tell the agent which restaurant to go to. You don't say anything about what other restaurants there are. You don't give any explanation as to why. You just say, you should really go to Arturo's. And that seems like a recommendation system that no one would use. And so why is that? I think there's several things that are going wrong here. One is that, and that's the second bullet on the slide, as I've been hinting at, it's not, the agents don't necessarily trust the principal to implement the policy they stated. So I want there to be more transparency in the systems I use. I want to see explanations as to why you think that's the right thing for me to do. And so I wanted to see, can we still get this regret bound while having something that's more transparent and relies less on the commitment of the principal. The other issue with the prior work is that it relies very heavily on agents being Bayesian rational, which means that they have a prior, that prior is correct, and they do correct updating based on the information and the policy that they know you're using. And so there's a question as to like, how believable is that, especially in these systems where agents come once and they interact once and as a tourist in a new town and go to some restaurant, like, are they really able to do this kind of Bayesian rational updating that is assumed of them? So in order to move away from those two assumptions, we introduce a model where agents are frequentists, which relaxes this rationality assumption. And the signals that the principal presents to the agents aren't a single recommendation of a single restaurant, but rather a subhistory containing the chosen restaurants and their reviews for some subset of the agents that came in the past. And the theorems that I will present to you are that we get a sublinear regret with a very simple scheme, and we can get optimal regret with a more complex layered scheme. And I'll state the exact regret bounds in a few slides. And I think one main idea here that is sort of something you could go recommend to people at these companies is that it's a good idea to group agents into focus groups when you're trying when you're in this learning phase. There's a bunch of related work. Primarily, I discussed the related work in the CS literature in the introduction, and this is a bunch of the related work that's largely from the economics literature. So if you're interested in this area, you could go look into some of these papers. I'm not going to discuss them here. Let me instead get into the technical part of the talk. So I'll present the model and some preliminaries. So I'm going to have, for the purposes of this talk, I'm going to focus on a setting with just two arms. And I'm going to assume that each arm has a Bernoulli mean reward, MUA, which is drawn from some interval between 1/3 and 2/3. Namely, I mean that the reward RA of an arm A is 1 with probability MUA and 0 otherwise. Now, in the paper, we can work with any constant number of arms, and we can generalize beyond Bernoulli mean rewards, but you can look at the paper for that. I'm going to label the arms such that mu1, arm 1, is the one with the higher mean reward. But of course, the principal doesn't know, and the agents don't know which arm is arm 1. And so that's the whole point, is that they have to try and learn which arm has the better mean reward. The agents are going to be indexed by time, t. And when an agent arrives, they are presented with a signal and choose an arm, a sub t, and then receive a reward RAT drawn from this Bernoulli distribution mentioned above. The signals that the agents get to see while making the choice of arm are subhistories. So that's formally a set of tuples consisting of a timestamp, the restaurant that was reviewed or the action that was taken, and the reward that was received from that restaurant. And so this is the data that the agent has access to when they're making their decisions. The behavioral model, I'm going to assume that the agents are frequentists. So that means when they look at all this data, H sub S, they're going to look at each restaurant in that data set and look at the number of pulls of that arm, so the number of reviews of that restaurant. They're then going to calculate the empirical mean reward that that restaurant received over that number of arm pulls. And then they're going to make some assumption about the quality, the true quality of the restaurant. So they're going to make an estimate, mu hat. And then they're going to decide to go to the restaurant which they have the highest estimate of its quality. So they're going to then go to the restaurant that has the maximum mu hat. And I'm going to assume that the estimates that the agents are forming, mu hat, get asymptotically close to the empirical means as the number of arm pulls increases. So if you see a restaurant on Yelp that has 3,000 reviews and 4.5 stars, you're going to assume that it's really likely to be a very good restaurant. Whereas if you see a restaurant on Yelp that has 2 reviews and 4.5 stars, you can make any assumption about it you want. So This is the behavioral model for the agents. I am not exactly specifying their behavior. There's a whole range of behaviors that satisfy this assumption. But the main point is that the the estimates get close to the empirical means as the number of observations grows. Now, you might think, okay, if that's the way the agents are behaving, it'd be easy for me to convince them to do anything I want them to do, because if I want them to go to Arturo's, I'll just select the reviews in which Arturo's was highly rated. And if I want them to go to Prince Street Pizza, I could just select the reviews in which that one was highly rated. And so to prevent the principal from fooling the agents in this way, from abusing their simplicity, I'm going to restrict the principal to choose signals that have a particular structure. I'm going to ask, first of all, that the signals are transitive, which means that if I see the data that if I see Christina's review, then I also see all the data that Cristina saw. I'm also going to assume that these signals are chosen ex ante, and this prevents the kind of trickery I was mentioning before, where the principal tries to show me only good reviews of the restaurant they want me to go to. So in particular, the principal has to decide up front that, for example, every agent that comes and writes a review on an odd day is going to see the history of everyone that wrote reviews on odd days, whereas the agents that come on even days see the history of people on even days. And now this is good because it prevents this kind of trickery. You see, like this structure was chosen before any agent came in the door. Now the principal, the yellow agent on the far right, is coming in the door, and the principal sees that in the path that the yellow agent would observe, the blue diamond arm is doing well. The principal might regret that because maybe the principal wants the triangle arm to get more explanation. So the principal would like to edit the history at this point and instead present the yellow agent with the even subhistory, and I'm disallowing that. So this model is, I think, nice from a like motivational perspective, in that I feel like frequentist behavior is representative of what agents might be doing in this kind of world, but also it has some justification in a sense that there's an alternate world in which only the even day exists. And from the perspective of somebody that comes in on an even day, they would be seeing the full history of that alternate world in which only even days existed, which means that the frequentist behavior that I've stated would be a reasonable assumption in such a world. And also we show in the paper that this model can be rationalized for Bayesian agents with appropriately chosen priors. That's a bunch of economics lingo. If you don't get it, don't worry. I actually think that I prefer the other justification that I discussed on this slide. Another thing I want to point out about the model is that we can interpret it as social learning. So there's a whole literature on how do I learn information by talking to my neighbors in a social network. And this is, you can interpret what we're doing here as a social learning problem in which the principal constructs the network and then lets agents engage in social learning. And so just to formalize the regret notion, this is the standard thing you're all used to. The regret is the optimal utility of the optimal planner that takes the best single action in hindsight, minus the expected utility induced by the policy, where this is in worst case over the realization of the mean rewards. And so there's several things you might try to do to solve this problem as a planner. Maybe you just show everybody every review that was ever written. And this can actually be suboptimal, because then if some are, initially everybody is equally likely to choose anything, and maybe their estimates are, say, the middle, They make no assumptions. But then as the reviews come in, maybe one arm gets very unlucky. Like one restaurant just has a couple of bad days in a row and their empirical mean plummets. And because there's enough reviews, the confidence intervals around the empirical means of the lucky restaurant and the unlucky restaurant could separate, and thereafter everyone would pick the lucky restaurant, the blue diamond in this example. And so we want to avoid that kind of failure. This is in the economics literature, they'll say that this is a herding type behavior. So the agents have herded on the suboptimal arm. Another thing you might try is, well, we can prevent herding by just not showing anybody anything until we have enough information to figure out which arm is better. So let's suppose that we knew the gap between the best and second best arm, that is how much better is the better restaurant. In that world, we could choose some number of agents K to have no history, and then thereafter show everybody the reviews of these K agents. And so you can use this theorem from statistics about distinguishing biased coins to show that if you set the parameters of this correctly, you can get a sublinear regret. So the optimal plan, as we've discussed, gets the T times mu1. So the optimal planner would just pull the arm, would just always go to restaurant 1, send everyone to restaurant 1 and get expected payoff of T mu1. This no history policy, well, the first K agents in the worst case are going to the worst arm. They get K mu2. And then the remaining T minus K agents are going to get, well, if we've successfully distinguished with those first K agents which arm is the better arm, which happens with probability 1 minus epsilon, according to that statistics theorem I referenced, then we get a payoff of mu1 because we know which arm to pull. And in the epsilon's probability case that we didn't manage to distinguish the better arm, then we get a payoff of mu2 from the T minus K ladder agents. And you can compute the difference of these two and note that it's with this parameterization I selected, log T over delta. So this is a standard result in multi-arm bandits, and it works here because these agents are just incentivized to always exploit all the information that they are presented with. But we want to get similar kind of bounds without using knowledge of the gap parameter delta. And so I'm going to show you a 2-level policy that gets regret T to the 2/3, a 3-level policy that improves on that, and an L-level policy that asymptotically approaches the regret of the best multi-arm bandit algorithms without incentive constraints. And one thing to note here is that it's well known in multi-arm bandits that if you're going to use a non-adaptive policy, the best regret you could get is T to the 2/3, which is what our 2-level policy is getting. And in order to improve on that, you have to use adaptivity, which means you have to, explore your options for a while and then sit back and think, do I now know enough to be confident in what the best action is, or do I need to do further exploration? So that's the adaptivity notion. And in order to break this T to the 2/3 barrier, we need to enable that kind of adaptivity. And it's kind of surprising that you can enable that in the setting I've presented to you, in the model I presented to you, because we're insisting that all the data sets that you're going to see are chosen ex ante. So I can't adapt to the specific data that I see. So how can I induce adaptivity? And I think that's the main innovation, technical innovation in this paper. But let me start with the T to the 2/3, and then I'll show you how I get adaptivity after you can see the simple solution. So the idea is to combine this full history policy I presented to you with the no history at first policy that I presented to you. In particular, I'm going to set a bunch of what I will call level 1 agents. These are my focus groups that I hinted at before. And in each group in level 1, I show everybody all the data of the members of their group. So you could think about this as a policy that says everyone who comes on a Monday is going to see the restaurant reviews of everyone else that came on a Monday. And everyone that comes on a Tuesday will see the reviews of everyone else on a Tuesday, and so on. And that would give you a set of groups. The information is not shared between the groups at all, so there's no sort of contamination here. And each group gets to compare the notes amongst themselves only. Now, this is because of that herding that I told you about with the full history. This is going to guarantee that each arm gets sampled with constant probability, because there's some probability that the red triangle arm got lucky, and there's with the remaining constant probability, the blue diamond arm got lucky. So each of these groups is going to guarantee at least one sample of one of those arms. And so with the level 2 agents, all the remaining agents that aren't in these focus groups, I'm going to show them the data of everybody in all the focus groups. And because the focus groups have provided samples of each arm, these level 2 agents are going to be able to distinguish the better arm and exploit thereafter. And so, you have to, this is the whole trick now, is to set the parameters such that you don't have to use knowledge of the gap in order to decide how many level 1 groups you have. And so you can do that. It's standard in the multi-arm bandit literature. And what we know is that if you have something like t to the 2/3 level 1 groups, then you can get a regret bound of like t to the 2/3. And the intuition here is that the level 1 agents are going to provide enough exploration to distinguish the better arm if this gap parameter is large. And if the gap parameter is not large, then I don't actually care if we didn't distinguish the better arm, because it doesn't hurt my regret all that much if everybody pulls the worse arm. So that's like the main idea for the proof, which you can then go prove to yourself if you want. You can interpret this as doing all exploration and then doing all exploitation. So this is an explore then exploit policy. The level 1 agents are doing the exploration, and the level 2 agents are doing the exploitation. And now I want to improve upon this regret bound. So I have a t to the 2/3 regret. I want to improve upon this. And as we discussed, this improvement is going to require adaptive exploration. So I can't put all my exploration up front. I'm going to have to do exploration interlaced with exploitation. And so let me describe how I do this in the context of my model, where I have to pick the information structure, like who shares reviews with whom before anyone comes in the door. How can I possibly get adaptation in that world? And the first idea is to just replicate my level 2 structure, my 2-level structure, multiple times, and then add a 3rd group at the top. So what does this do for me? Well, the level 1 agents, as before, are providing exploration, and the level 3 agents, as before, the top level agents, are doing exploitation. And now this middle level is going to end up exploiting if there's a clear winner, and otherwise they provide additional exploration. So how does that happen? Well, we'll do this again using a case analysis based on this gap parameter. If the gap is very tiny, then I get low regret even if everybody picks the worst arm. If the gap is very large, then each level 1 group is going to be able to provide enough information for an observer to determine the better arm. And so the level 2 and 3 agents all pull the better arm. Now, what about a medium gap case? So you have to work out the parameters, but small, negligible, and large, there's still stuff in between. If the gap size is medium, then each individual set of level 1 groups, like each single level 1 group doesn't provide enough information to determine the better arm, but in aggregate across all the level 1 groups, you can determine the better arm. Now, the level 2 agents don't see the entire level 1. They only see a subset of level 1. So they're kind of screwed because they don't see enough information to make this distinction. But the level 3 agents do see everybody in level 1. And so they're able to pull a better arm. And the final remaining case is what we call the small gap case. And this is really what is the adaptive exploration. So in the small gap case, for each arm, so this is the case in which the level 2 agents are providing very useful additional exploration because the gap wasn't large enough for us to distinguish the better arm. And the way that they do this is for each arm, there is a level 1 group such that that arm gets lucky in that level 1 group, and the other arm is unlucky in that level 1 group. And this guarantees, because of our frequentist assumption on behavior, that for everyone in the level 2 group observing those level 1 agents, they estimate that their estimate of the lucky arm is higher than their estimate of the unlucky arm. And so that corresponding level 2 group is going to provide additional exploration of arm A. And notice that this only happens in the world in which the gap is so small that some arms get lucky in one group and unlucky in other groups. And so this is going to induce the level 3 agents to pull arm 1 because they get to see all the additional exploration, not just the exploration from the level 1 agents, but also the additional exploration from the level 2 agents. And so that turns out to be sufficient to get us to a t to the 4/7 regret bound. But of course, we'd like to get t to the 1/2 regret bound in order to match the regret bounds of the multi-arm bandit literature. And so in order to do that, we're going to have to be able to distinguish finer and finer gaps between the best and second best arm. So let's consider a gap delta, and we want to be able to get a level L that can distinguish arms, which is the better arm when that gap is that delta, right? So I'm going to create, for each level, it's going to have the job of doing additional exploration when the gap size is delta. And one attempt, the first attempt that might come to your mind for how to do this would be to create an L-level emery tree. Now, this is going to be successful at distinguishing finer and finer gaps. So the kth level in this L-level emery tree will indeed be able to distinguish a fine gap between the best arm and the second best arm. But the problem is that there's exponentially many leaves in this tree, and all of those leaves are inducing high regret because they don't have enough information to make intelligent choices. And also, you know, it's always good to step back from the math and remember why we're doing it. So it's also the case that all of these level 1 groups, if we were to implement this policy for a recommendation site like Yelp, the large fraction of the population wouldn't be getting any value from Yelp because they wouldn't be seeing any other reviews, right? All of these level 1 groups see just a handful of other reviews, and that's really bad. What you'd really like in a system like Yelp is to have everyone see almost all of the reviews that are in the system when they come into the system. And so instead, we are going to present a policy that interlaces information between groups. So for any level L, I'm going to have my what I call explore groups. And these are groups that will see the same history. And then I'm going to have my exploit group that see different history. So this is a pretty complex interlacing structure. But what you can check is that the groups that I highlighted in red, they both see the same subhistory with the way that I've drawn my connections. And what that means is that, what that means is that if in that subhistory, say the gap parameter is pretty fine, so that an arm is likely to get lucky in some subhistory. So if in that subhistory the triangle arm gets lucky, then both the groups in the middle level, circled in red, will provide additional exploration of the triangle arm. Similarly, the diamond arm has the other two groups have a unique subhistory. And so if the diamond arm gets lucky there, those other two groups will provide additional exploration of the diamond arm. And then the top level groups get to see some additional exploration of both arms. And so in this way, we're able to reuse information in order to give everybody additional exploration rounds without at the same time blowing up the number of agents that have a low, are trying to make decisions with a very few reviews to base their decisions on. And so this turns out to enable a policy that gets regret bound that approaches t to the 1/2. And the main idea, as I've been emphasizing, is that we need to reuse information by interlacing groups. And I just want to point out that this is pretty subtle because we need to make sure that the information doesn't contaminate, right? It was important that there's disjoint subhistories among certain parts of the population such that we don't get contamination or herding behavior across the entire population. So that's the main sort of technical result in the paper, but let me step back and give a little bit more of a high-level discussion of what's been going on here. The main result that I presented was how to get optimal regret with this selective data disclosure model with frequentist agents. And so I think the model itself is nice. It relaxes the commitment assumption of the principle, loosely speaking, and that's because the principle has to back up the recommendations that he or she is making with evidence, namely subsets of reviews. And if you wanted to monitor the recommendation site, you could have some third party check up with the reviewers and make sure that those reviews were in fact legitimate and things that they actually wrote. The other thing is our model relaxes this rationality assumption. That's because we're using these frequentist agents instead of assuming Bayesian prior with Bayesian updating. And finally, we're robustly achieve an asymptotically optimal regret. The robustly here is because the principle isn't making any assumptions about the distribution of mean rewards. And we get a regret that approaches the regret of some principle who knew the distribution of mean rewards. In fact, we approach the regret of the omniscient planner at a rate of root t. And so the main ideas we saw, each main idea helped improve the regret bounds. The first main idea was to use focus groups of agents to explore arms. The second main idea was, and that was the two-level policy. The second main idea was to use group aggregators to refine the exploration. And so this provided us with that one round of adaptivity, and you could interpret the level 2 agents in that 3-level policy as having the job of aggregating the reviews of a bunch of focus groups. And so you might want to have, a hierarchy where some people are in charge of aggregating reviews of a bunch of subgroups and passing it up to their superiors. And finally, we looked at an L-level policy where we saw that we needed to interlace connections in a special way in order to reuse exploration and reuse information among these focus groups and their higher levels. So thank you for your attention, and I'm happy to take questions.
Thank you, Nicole, for your very nice talk. So does anyone has a question for Nicole?
I have a question.
Yes,
thank you, Nicole, for the great talk. what happens in the real case of multi-armed bandits? So not just two arms, but many restaurants or many. Does this change the width of the tree, or also the amount of levels, or?
So it's going to change, in terms of the results, it's going to change the constants in the regret bound. In particular, so I said at some point that we can extend this to a constant number of arms, and that's because the regret bound depends exponentially on that parameter. So the constant in the regret bound is like 2 to the number of arms. And in terms of the structure of the policy, I would have to think a little more deeply about that. I believe it would increase the number of level 1 agents. So the number of focus groups, both in terms of the number of focus groups and also each of them had a path length.
Yeah. Okay. Thank you.
Anyone else has a question to Nicole?
I have a question. Hi, Nicole. For a great talk. So are you assuming that every agent pulls the arm only once, yes? Because
Yes, exactly. So this is more appropriate for, like, you know, tourists on TripAdvisor than someone who lives in New York City going to pizza restaurants. It's important that the agents are short-lived in the model, but it's also like the extreme of what highlights the issue that the principal is facing with inducing exploration. If the agents were as long-lived as the principal, then we would just all be doing multi-arm bandit algorithms optimally for our own, you know, exploration. And so that's one reason, like, or one motivation for studying this extreme where every agent comes in only once.
thank you.
Anyone else has questions for Nicole? If not, I have some question for you. So first, let me try to see if I understood. So exactly this point of frequentist and rational. So that's the parallel, right? Rational goes always for the best possible choice. And what you refer to as frequentist is the person that risks a bit to experiment, is it?
In a sense, so the frequentist is going to just look at the empirical mean of the data set. But if I had a prior, like if it was much more likely that a churros is much better than Prince Street Pizza, what I should do is I should look at all of the data, and also not just the data itself, but the reason that I received that data, which is, in other words, the algorithm. And I should do a Bayesian update using my prior to get a posterior. And then I should look at the posterior mean reward of these two restaurants and pick the better one. So that's sort of like the standard econ approach, right? Like I would assume that every agent knows the distribution from which these mean rewards are drawn, and then looks at the data set and does an update based on the distribution of mean rewards, and then looks at the posterior means and picks the one with the highest posterior mean. My frequentist agents are not doing that. They're not, and the reason they're not doing that is they don't start from a prior. Instead, they start from the empirical mean. And then I let them, then I let in a class of behaviors. You could be optimistic about one restaurant and pessimistic about another. It's not that you're being risky, like in your own mind, you're always going to the thing you think is the best. But I'm allowing you to have biases in various arbitrary directions, so long as enough evidence convinces you. Is that clear?
See. Yes, it improved my understanding. And yeah, that was one doubt I had. And the other thing I wanted to ask is, so the users, they arrive online. So it's a kind of an online setting. On the other hand, you have these groups. So I imagine that, well, you said, right, that when a user arrives, you want to decide where it enters without, it does not depend on the user himself, right? It's
doesn't depend on the user or the results of the past reviews. Yeah.
Or the results of the past reviews. Yeah, so I understand the independence, but I mean, you cannot just, because these groups, they have sizes, right? That's the whole thing, right? They're proportional, of course, because it's online, right? So is it something like this that's going on? So you are deciding some fraction of whatever number of users you have is in group 1, group 2, etc. And then the users arrive and are placed in one of these groups.
Yeah, and I say, like, I'm going to assign you to a group in a round robin fashion, and I commit to that too. So you arrive, and if the next group that needs a member is group 5, then you're assigned to group 5.
Right. And so from your knowledge of how these algorithms are used, do you truly, because I think, so you know better than me that users are not the same, right? There are users that behave in more a certain way, but that's again maybe against your assumption that the user is one shot user, right? So you don't have the history of the user, do you? You don't.
Yeah, so you don't have the history of the user, and I think maybe what you're hinting at is that users are heterogeneous in their preferences. So maybe, like, I just usually prefer Chinese food unless the Italian restaurant is really fantastic, and so I'll tend to go to Chinese restaurants unless I hear something about an amazing Italian restaurant, and you're the opposite. And then because of this heterogeneity in our innate tendencies, we're sort of providing exploration for one another, right? Like, I'm naturally exploring Chinese and you're naturally exploring Italian, and then we're going to find the diamond in the rough between us, because like one of us will discover the best Chinese restaurant, the other will discover the best Italian restaurant, and we'll tell each other about it. And in such a world, there's a question about whether there's even a place for the principle. Like, do we need any sort of coordination, or does this heterogeneity in our preferences provide enough exploration on its own to get good regret balance? And I look at that a little bit in a paper. It's actually pretty hard to come up with a model that's very convincing there, because you have to create a structure in which our preferences are somewhat aligned, right? If you hate Chinese food, no matter what it is, then me exploring the Chinese restaurants is useless, right, for you. And so in this paper, we come up with a way to, and this is a dub paper, I can send it to you later if you want, but we come up with a way to interpolate between how closely aligned our preferences are, and we ask, what is the optimal amount of diversity in a society to get good learning? Yeah.
Oh, nice. Esteban, I see you raise your hand, so go ahead.
Yeah, just one more question. What about the dynamic version of this? So when with your strategies, if a new restaurant arrives when the exploration part has ended, it would never have the opportunity to be explored. So how do you thought that this could be managed?
Yeah, so that's definitely an issue. I'm assuming all the restaurants are available up front before any user comes in. If restaurants come in over time, I imagine that it's a good idea to do no history at first kind of thing, right? Like, you don't want to let people herd on the restaurant was unlucky for 2 days in a row. And so you probably should provide no reviews until there's enough reviews to have some confidence in them. And you actually see this happening. So like Airbnb, for example, won't give you reviews of a stay until there's enough people staying there.
But you introduce them in the tree, like from the side when they arrive, and they have their own face, level 1, or
we haven't studied that. Like, that's I think, but that would be my guess as to what would be the right solution.
Okay, thank you.
Okay, so if nobody has other questions, then We should thank Nicole. So everybody is invited to open their mics. And